Assalamualaikum warahmatullahi wabarakatuh. RABI'ATUL. Today, we are from Group 5. We'll present to all of you from our previous site visit about condensing liquid nitrogen Hpge detector cooling system. For host code SSCP4453, low temperature physics and superconductivity. I will introduce to all of you my group member. Will consist of 6 people, including me, Siti MARYAM, and I have 5 friends, RABI'ATUL ADAWIYAH, PUTERI EMILYA, NABIHAH, HUSNA, and also Siti NORFAZLEEN. During our site visit on 19 May 2026, our lab assistant, Encik Saiful, has demonstrated the operation of the cryogenic system, including the cryostat and cooling mechanism used for the Hpge detector. The cryostat acts as a vacuum-insulated chamber that maintains low temperature stability and protects the detector from thermal interference. Other than that, the Mobius system also reduced the need for frequent manual liquid nitrogen, the refilling by using an automated cooling and recycling process.
My name is EMILYA and I will explain the cryogenic technology used in the nuclear laboratory. The system used is the ORTEC Mobius Hpge detector cooling system. This system applies liquid nitrogen together with mechanical cryogenic cooling to maintain the high purity germanium or Hpge detector at a very low temperature, which is around 77 Kelvin or negative 196 degrees Celsius. The cooling process is very important because the germanium crystal inside the detector is highly sensitive to heat. So if the temperature is too high, thermal noise will increase and this can affect the accuracy of the measurement. By cooling the detector to cryogenic temperature, the thermal noise can be greatly reduced. As a result, the detector can produce more accurate and high-resolution gamma-ray spectroscopy measurements. The figure shown here presents several types of Mobius cryostat systems used for detector cooling in nuclear laboratory applications.
Next objective. First, to understand the application of cryogenic technology in high-purity germanium detector cooling system for nuclear radiation detection. Second, to study the operation and function of the cryostat, liquid nitrogen cooling and gamma spectroscopy equipment used in the nuclear laboratory. Third, to relate the concept of low temperature physics and superconductivity with real industrial application in radiation detection and nuclear instrumentation.
Next, I will explain the physics concept investigated in our study related to cryogenic technology and Hpge detector system. Firstly, the project aims to understand the application of cryogenic technology in Hpge detector cooling system used for nuclear radiation detection. So Hpge detectors require extremely low temperature to reduce thermal noise and improve detection accuracy. Second, we study the operation and function of the cryostat liquid nitrogen cooling system and gamma spectroscopy equipment used in the nuclear laboratory. The cryostat acts as an insulated chamber that maintains very low temperature, which liquid nitrogen is used as the cooling medium to keep the detector functioning efficiently. Lastly, this project relates the concept of low temperature physics and superconductivity with real industrial and scientific application, especially in radiation detection and nuclear instrumentation. So through this study, we can better understand how cryogenic systems improve detector sensitivity and stability in nuclear measurement.
Moving on to our expectation observations for this experiment, we have broken this down into 3 core objectives that connect the physical technology with the underlying physics concepts. First, we will focus on the hardware itself. We expect to observe the operations of the ORTEC Mobius Hpge detector cooling system. By looking at this specific setup, we'll gain a direct understanding of how advanced cryogenic technology is integrated into modern radiation detection systems to maintain extreme low temperature environments. Second, we want to bridge the gap between the hardware and the data quality. Specifically, our goal is to understand the role that liquid nitrogen and caustic play in suppressing thermal noise. Our high-purity germanium detectors have a relatively small band gap, meaning room temperature thermal energy can easily excite electrons and create massive background noise. By cooling it down, we drastically reduce this leakage current, which is absolutely critical for achieving high-resolution, accurate gamma-ray detections. Finally, we will look at the bigger picture. We aim to relate this low-temperature physics concept to practical, real-world applications in nuclear radiation detections and spectroscopy. This will allow us to see how maintaining these strict cryogenic conditions directly impacts the precisions of isotope identifications and spectral analysis in this field.
Safety considerations. Number 1, wear proper personal protective equipment (PPE) when handling liquid nitrogen. Number 2, avoid direct contact with cryogenic liquids and cold surfaces to prevent frostbite or cold burns. Number 3, ensure the laboratory is well ventilated to prevent oxygen deficiency caused by nitrogen gas evaporation. Number 4, never store liquid nitrogen in a sealed container because pressure buildup may cause explosion. Number 5, handle cryogenic system carefully and follow all laboratory safety instructions during operation of the Hpge detector and cooling system.